stopping me in case there are any questions. Oh, looks like it's a little. Do you see the entire set of slides, or do you see like is it cut at the end, at the bottom? Yeah, okay. Let me see if I can change that. I don't know why this is truncating it. That's not great. Yeah, let me make it full screen and then hope for the best. All right. No, I think now you can see the whole thing. Yeah, that's yeah. Let me forward a slide. Yeah, you can see the whole thing. Yeah. All right. Cool. Great. Yeah. The only problem is now I like don't have my browser on, so yeah, I really need, if there's any chat, just have to stop me and then we can do this, because I was trying to have the things in different windows. Sure. Yeah. Okay. Yeah. Let me get started then. Thank you so much, David, and everyone for being here. It's really my pleasure. Let me introduce myself first. My name is Vagelis Paplexakis. You see the name. It's a long name because it's Greek, and I'm an associate professor at UC Riverside at the computer science department. And today, what I want to do is I'm going to talk a little bit about kind of an overview of the research that we do in my lab that has the general umbrella of what we call multi-aspect data science. Feel free to interrupt at any point if something is not clear, if you have any questions, I would like that to be as interactive as possible. And so don't hesitate to interrupt. I just, may need some help going from one screen to the other to see your question, but that will happen. Before I go in the kind of formal part of the talk, just give you a brief introduction of sort of my background. So I was born and raised in Greece, in Athens, and then I did my undergrad and my master's in Crete, at Technical University of Crete, which is this island in the south. And then I flew all the way to an exotic place called Pittsburgh, in Carnegie Mellon University, and I did my PhD over there. And so through that time, I did a couple of internships in the summer, and I fell in love with California. And so when the time came for me to find a job after the PhD, I found a really nice job at UC Riverside, and I haven't looked back since. And so I'm really glad to be here and sharing some of our work with you all. And so the way I like starting talks about data science is by showing those two numbers. And let me just switch to the chat so that I can see, like, does anybody know, and feel free to type in your answer, what are those two numbers representing? Have you seen them? I mean, obviously you've seen 7 plus or minus 2 before. We've seen those numbers in many contexts, but can you think of a context that those two numbers go together, and 7 plus or minus 2? And feel free to just type in your answer in the chat. I can see the chat now. Don't be shy. Confidence interval. Yeah, so that's indeed some kind of interval that kind of gives us, a range, right? When you're solving a quadratic formula, well, that ends up being kind of a solution, right? But that's not what we're dealing with here. It is more of a range, but a range of what? Can anybody think? Can anybody imagine? Just a couple more seconds in case there's anybody typing up an answer. So let me, range of solutions. Well, solutions to what? To an equation? It's a little more philosophical, if you will, than that. And let me just, go back to the, oops. All right, sorry about that. My Chrome decided to fire me, but I came back. Let me just continue, right? So basically, this is a result from cognitive psychology that talks about the limitation of humans in retaining things in their working memory. So 7 plus or minus 2 are the things that we can retain and kind of argue about and understand while being presented, right? And so now, how does this work into data science, right? So in today's kind of world, we have tons of data, right? We take pictures with your phone, you interact with other people on social media. There's tons of content online, news and articles of any sort of kind of flavor. There's even scientific data that are being generated. There are tons and tons of kind of petabytes of data, right? And so the way that you want to look at data science is this set of tools in the middle, this is right in the middle, that takes in all this kind of humongous amounts of data and distills it into 7 plus or minus 2 insights, right? And so that's how you want to look at it, right? Where data science is the set of tools that maybe uses AI algorithms and machine learning algorithms that distills the things you need to look at as a human being, or as a scientist who is interested in the scientific data, in order to make some value out of your data. Just to give you an example, right? Very kind of everyday example. Let's say you take a picture of this set of latte art kind of coffees, right? And inside would be, well, I'm 100% certain that this is a picture of coffee, and maybe 95% of this is a latte. And if my AI is a little bit kind of pretentious, it will say, oh, 80% could be a cortado, right? And so, we all have this capability in our phones now where, we take a picture and some machine learning algorithm is able to tell us a few things that are useful to us about it, right? It's important to remember that on the one side we have data, on the other side we have insights, right? And data is not just a monolith, right? It comes in different kinds of flavors, and it comes in different kinds of configurations and scenarios. And a very fundamental kind of way of looking at data that we may have at our disposal is what we call the level of human supervision, right? So how, and I'm going to give you an example, because I don't assume that you may have heard those terms before, but let's say in the example where we're understanding what is there in a given picture, what supervision would be is to take, let's say, 1,000 pictures and sit down very carefully, me and maybe 10 other friends, and actually tag the pictures with what we see to be in there, and then instruct the machine learning algorithm to learn that association and to be able to understand, and generalize to pictures of coffee that it has not seen, right? So that annotation that we did and sat down carefully and spent time is supervision, right? And the other end of the spectrum is, let's say, somebody giving me 1 million pictures and telling me, well, I don't know what those pictures are showing, but your job is to identify the things that are in those pictures. And so my answer would be, well, what I found was 10 different things that are being depicted here. And here's one group that is all looking the same. Here's another group that all looks the same, but very different from this other group, and so on and so forth. And so I'm discovering essentially the structure in the data. And in fact, this supervision is kind of a spectrum. And you want to see, like, getting supervision sometimes is not just a matter of time and effort, but it can actually also be an impossible or ill-defined task. We may not know exactly what we're looking for in the data, and so it's impossible for us to even ask someone to tell us what is in the data, right? So our methods should be actually driving that understanding and discovery, right? Are we okay so far? Are there any questions about this? I'm assuming no, but again, feel free to interrupt if there are any questions. All right. Now, we're going to go to a simple example and a very popular one, right? So I'm assuming everybody is familiar with, movie and video recommendation, right? So you may be on Netflix, Disney Plus, whatever platform, you may be kind of subscribing to and watching, your favorite movies and shows on, right? And this is essentially, this is how those platforms to this day are doing recommendation, are able to understand your preferences and give you actually meaningful and valuable recommendations to you, right? So let's take this example. This is me, and this is basically, I watch those movies and I like them a lot, right? So if I have a star here, I like those movies a lot, right? This, basically, like, I have 8 dimensions here. I have 8 movies, right? And so you can express my viewing history and my viewership patterns and whatever as a point in 8 dimensions, right? Now, I don't know about you, but I can see 1, 2, and 3 dimensions. But when it comes to more dimensions, I have trouble, right? And what does it even look like, right? So we cannot even kind of visualize it, right? So and of course, Netflix and Disney Plus and whatever don't have only 8 movies. They have thousands and thousands of movies. So in fact, my viewing history would be a vector in thousands of dimensions. And so this high dimensionality is really kind of the deluge of kind of data that we see, that I was talking about in before. And what we need to do now is we need to understand how machine learning and data science can distill it into a few things that we can understand, right? And so thankfully for those companies, I'm not the only one who's watching, right? So we have other folks watching a bunch of movies and rating them, right? So we have ET here watching them. If you don't know who that fellow is the star of this movie right here. We have one of the Minions watching it, and he only liked the Minion movie and School of Rock. And then we also have Jack Black, who also has the same opinion as the Minion, right? And so given now all those multiple users in multiple movies, we have enough data to try to understand emerging patterns and try to understand whether there are things that are more compressible and summarizable and fall under this 7 ± 2 kind of requirement that we have, right? And if we kind of look a little more closely into, if you try to see what patterns may even emerge here, right? You may kind of, if I color those movies and stars in blue and kind of pinkish, right? Then you can kind of see that, hey, those blue movies are kind of sort of similar in terms of maybe being adventures, and those other movies are maybe kind of sort of comedies, right? And so, in fact, you can actually say, well, there's only 2 things going on here. And those 2 things are adventure and comedy, right? So if I feed this into this kind of machine learning algorithm, one thing you can tell me is, you know what? Your users don't live in this 8-dimensional space. They actually live in much smaller dimension. They either like adventure or like comedy. And those are the 2 things that I found in the data, right? And mind you, this is not necessarily what was the intent of the movie producer in the studio. This is the way that the viewers watch the movies, right? And so that would be here the 7 ± 2, and actually 2 here insights, right? And so what we were able to do was to actually transform my profile and everybody else's profile in 2 dimensions, that now those dimensions are insightful, right? One is adventure, the other one is comedy, right? And if we had more data, we could discover horror and maybe thriller and other kind of more subtle genres that emerge through viewership, right? But this is exactly how recommendation happens. Now, how, you can now visualize, right? Now this is 2-dimensional grid, right? So hopefully we all seen, at least in 2 dimensions in algebra, how do we understand objects, right? So if we have this being the adventure axis and this is the comedy axis, ET and I are in the full-on adventure, no comedy, and Jack Black and whatever his name is are in the full-on comedy, no adventure space. And we can actually do the same thing for the movies, right? And again, this is for the sake of argument. I'm not arguing that like there's no adventure in the Minion movie or whatever, right? But for the sake of argument, this is how those movies would fall into that space that was discovered by the machine learning algorithm. And why is this useful is because now we can use that space to find movies that I would like, right? Because maybe there's some new movie that I have not seen for which we know where it falls in this space. And then we can find how good of a match it is for me, right? So let's say that's basically how we're going to decide, or Netflix is going to decide which movie to show me next, right? So my profile is 0 comedy, 100% adventure, right? And we want to see whether we should watch Moana or Home Alone 1, right? And it so happens that, basically we need to see how good of a match Moana is to me and how good of a match Home Alone is to me, right? And how do we compute this match? Well, this is how we're going to use those dimensions, right? So essentially, let's say this machine learning algorithm told us, well, Moana is 0.2 comedy, 0.8 adventure, and then Home Alone is 50-50 comedy and adventure, right? And this is my profile. So here's where linear algebra is extremely useful, because what we're going to do is we're going to take the inner product of my profile and the movie profile, and we're going to multiply them, right? So the match between me and Moana is basically a 0,1 vector times a 0.2, 0.8 vector, right? And so this is basically 0 times 0.2 plus 1 times 0.8, right? This is called the dot product or inner product, and this is basically what it amounts to, right? And similarly here, 0 times 0.5 and 1 times 0.5, right? And so if you end up doing the math, then Moana gets a 0.8 because the adventure wins, basically. And so I would compare those numbers, and Netflix would compare those numbers, and would say, you know what, you should watch Moana because that is a better match to the profile that you've just given me. And of course, if I end up watching it and I do not give it a star, I don't like it, right? Then my profile will be recomputed, and Netflix may have a different answer for me later on, right? But this is essentially how, even to this day, recommendation happens, right? And of course, this magical box in the middle that computes this profile is something that is an active area of research. But essentially, once we have this kind of profile for the user in the movie, all we need to do is compute this match, and we just get the winner. And this is how we do it, right? And so this is one example where, hope you all saw how kind of high dimensional vectors and algebra and so on are extremely useful notions in this whole business right here, right? And again, I'm going to pause a little bit in case we have any question. See if there's anything on the chat. So Eugene just asked a few moments ago if a computer can't pick out information and so on. Do you want to expand a little bit on this question? What do you exactly mean by that? You can also unmute yourself if you would like to. All right, maybe we can get to this question in a bit, but essentially, it's really hard to learn I'm assuming that you're referring to supervision versus unsupervised learning, right? And so most of the stuff you see in, computer vision and all those things that work really well are the product of supervision, right? And the latest advances you see in those ChatGPT models are a mix of things that we do without any supervision that try to understand what is in the data and how we can best represent it. Same thing we did with the movies. And a lot of very, very meticulous supervision. So OpenAI has paid tons and tons of money to people who their job is to basically teach ChatGPT to solve algebra problems or coding problems, right? And of course, the base of it has figured out representation of knowledge, if you will, in an abstract way. But then how do you make this actionable? Then it requires a lot of additional cleaning and work that it cannot be really done on its own right now. I suppose that was the question. But if I misunderstood the question, feel free to ask again. So let me just go back to my slides and now kind of go back to the title of my talk, which is multi-aspect data, right? So we saw data science, we saw data. What is multi-aspect? What does this thing even mean, right? So you can think of it as kind of introducing the plurality and heterogeneity of data that we have in the real world, and kind of not simplifying the representation of the data that we have. For example, let's consider we have a social network. Like we have friends or folks just talking to each other, communicating with each other, and normally a normal data set would just stop at that, and you just say this fellow right here talked to this lady right there, right? And so a multi-aspect data set would also include, for example, the means of communication that they use. So those two people used email, and those two people used a phone call, right? And so why is this useful? Well, let's say that we're interested in finding closely connected groups of friends, right? It's important to know whether those friends use email to communicate or use Snapchat to communicate, right? Because that would give us the sort of better understanding, better insight on what are the demographics of the group, how close how friendly they are, right? Maybe they're work acquaintances and they are emailing each other from home, right? Because they have things that they need to finish from work, right? Whereas if you're texting each other, maybe you're closer friends, right? Other example would be, whenever you're consuming content online, right? Typically, a plain data set would be, oh, here's the text of this article, right? But in fact, an article online is more than text, right? It has a bunch of images. Now it has videos. It has a lot of things, a bunch of ads here and there. And all those things are telling you something potentially interesting about this article. And we'll see an example of that later on, right? And so essentially what we do, what are we interested in those things? In addition, we're interested in kind of having in multi-aspect data analysis also introducing the human element, meaning how are we able to distill those more complex data sets into the 7 plus or minus 2 insights, right? So that we can explain in an easy and intuitive way to a human consumer, right? Whether that's a user or whether that's a scientist collaborator that wishes from us to analyze their data and help them with the scientific discovery, we need to be able to explain to them the solution, right? And how do we do all that with having very limited human supervision, right? Where we cannot afford, or there's no possibility of us to kind of have those, millions and millions of annotated data sets that we can use to do this supervised learning, right? So those are the kind of the questions that are in the center of the stuff that we work on, right? And my lab, the multi-aspect data lab at UCR, we basically kind of move between core kind of algorithmic research in modeling and representing and analyzing those heterogeneous, complex, multi-aspect data sets, and applying all those algorithms to a number of kind of high-impact real-world problems, including misinformation on the web, a bunch of applications that have to do with physics and gravitational wave detection, precision agriculture. We have railway safety and transportation recently, and cybersecurity being some of the main applications that we kind of care about. And what I'm going to do in the next few minutes is kind of give a small, brief overview of kind of a few of those applications, giving you kind of some examples and some pointers for kind of further investigation. And so that's one, right? And the first one we're going to see is this multi-view graph analysis, right? And if you have not heard the term graph, a graph is essentially a mathematical structure that consists of nodes or vertices. You can look at those faces as those nodes or vertices that are connected with what we call edges, those links, right? That's all there is to it. Of course, there's a lot of theory behind it and so on and so forth, but this is essentially capturing social relations as we were talking about before, right? And so a very useful thing that people have done throughout the last few decades is to kind of represent a graph as a matrix. Now, just out of curiosity, how many of us have kind of seen the matrix before? I'm assuming that in your algebra course, you probably have seen what a vector is that I was talking about before, right? Can you kind of I want to calibrate how much I can assume, or I just describe. Yeah, so do you want to? Okay, so that means probably you've seen, right? So a matrix is essentially this table right here, right? That kind of captures information that, in this case, it captures whether there's a link between this fellow and that fellow. So if we have a value here, that is essentially the presence of a link of an edge in the graph, right? And that's basically also called the adjacency matrix, right? And this is a very fundamental thing in graph mining, where basically we can now use a lot of powerful tools from linear algebra that some of those things you may have seen, but most of them probably you'll see in the first few years of college, but then you'll get a head start, where basically like we can now try to understand what is the amount of hidden information in this kind of data set. And it all boils down to this question right here. Again, I'm not gonna assume, again, maybe show of hands, how many of you have heard even this notion of rank? Have you heard those before? This is a little perhaps more advanced concept. So essentially, not really. Okay, that's fine. That's fine. So a matrix, any matrix like this, has a number of properties. And one of the most important properties is what we call the rank. Now, when you take a linear algebra course, the definition of a rank would be basically something like, oh, the number of linearly independent columns, blah, blah, blah. That's a very precise definition. That's kind of boring, though, for what I'm trying to say, right? So what I want you to take from here is that the rank of a matrix is also essentially related to the number of elementary patterns that this matrix has, meaning that we can define the simplest possible matrix ever as what we call a rank 1 matrix. Rank 1 means it's only a product of two vectors. Like, there's not a lot of information in there, right? Two vectors, if you multiply them this way, you make a matrix. That's a rank 1 matrix, right? That means that the amount of information that it has is very limited, is exactly one important thing. And so if you add those rank 1 things up, then what you're getting is basically something that is of higher rank, right? And the higher the rank now relates to how many of those important small things you have, right? And so why now am I talking about this? It's because we essentially use this notion of rank and try to extract those elementary components of a matrix, or what we'll see later is a tensor, through mathematical algorithms that basically try to express the data as a sum of those elementary things, right? And so this is very essential in analyzing basically any kind of data set, right? So anything you'd want to do, just anything you'd want to do in data science and machine learning will, under the hood, involve a lot of linear algebra. And so this is something that you certainly need to take into account while you're kind of preparing for your studies, and make sure that, like, algebra and probability and statistics and calculus, those are kind of, important for when you go for a machine learning course. But linear algebra is kind of hidden everywhere you look, right? And I did not know this when I was taking linear algebra as an undergrad, but now hopefully you'll hopefully remember that when you're taking linear algebra in a year or 3 years from now. But let me just kind of say that, essentially, if you have, let's say, adjacency matrix like that, there are good algorithms that can break it down to those elementary pieces. And so now the name of the game is give me this data, and I'll try to find all those elementary pieces for you. And each one of those pieces refers to a community of people, right? And so that's kind of what would be what we were doing in a normal data set, right? However, we have multiple such data sets, right? We have multiple such matrices, multiple such views of the data. And problem is that, if we kind of ignore, and let's say we sum those up, right? And we say, okay, let me just take an aggregated version of this, right? Then we kind of lose the fact that, oh, those people are texting and those people are emailing and so on and so forth, right? So we ignore this important structure that hopefully will be useful to us, right? And so how do we, not ignore the important structure? Well, the answer, my personal favorite answer, which has been the work of my lab for the last X years, is what we call a tensor and tensor decomposition. And this is quite advanced of a topic, but doesn't need to be intimidating. Essentially, a tensor, you can imagine this as being a multi-dimensional matrix, right? So if you slice this into 3 slices, you get those 3 matrices that you had before, right? But now you have a 3-dimensional object that represents all the information together. And you can have 4 dimensions, 5 dimensions, as many dimensions as your problem requires, right? And so now the idea is, how do I extract information in the same way from this type of data, right? And this is tensor decomposition is what this problem is called. And it is a why is this an interesting and important problem is because it has applications in a really diverse set of domains. So early on, almost a century ago, those methods started being developed in psychometrics, which is basically the analytical statistical component of psychology, where you have, let's say, questionnaires, and you get folks to answer certain questions, but then you try to understand individual differences and personality types and so on and so forth by analyzing this data. And so subsequently, those methods were adopted and rediscovered in chemometrics, which is the chemical data analysis field. And years later, signal processing, anything that has to do with communication systems and how, let's say, you can improve the way that your phone, for example, decodes information that is received by its antenna and so on and so forth, and much, much later in machine learning and data science, right? And so the fact that those methods have been rediscovered so many times, and mind you, at the time they were being rediscovered, it's not that those folks were, aware that other folks had discovered those methods. You couldn't just Google, oh, let me find this thing. You had to go to the library, had to actually find whether there's a paper that does the same thing as what you're trying to do. And so all those rediscoveries were kind of organic in the sense that people were there was a need for people to represent data this way and analyzing data this way. And that's what fascinates me, and kind of one of my kind of goals is to try to see how far you can push the application and utility of those kinds of methods as far as data science and machine learning goes. And one example of such kind of how far can you push and how much you can revolutionize a field is from this application in Chemometrics. So this guy down here, Rasmus Bro, that's his actual name, but he's also a good friend of mine, so I think I can call him Bro in multiple kind of semantic contexts. But basically, his whole, like the last 25 years plus of his career has been focused on pushing how much you can kind of use this multi-aspect modeling in order to advance life sciences. And so I'll give you an example. Let's say you have a chemical mix, and that chemical mix can be as simple as, let's say, a beverage, or as crucial as, let's say, a stool sample, where you want to find early markers of cancer, right? And so having this chemical mix, very important thing is to understand what kind of chemicals are in that mix, right? And a very popular way in chemometrics to do that is to shine different wavelengths of light into that mix and record the response, and kind of that becomes our data, right? Because for different wavelengths of excitation, you have different wavelengths of emission, and then you have different samples over time, right? And so that becomes this three-dimensional structure, right? And it turns out really beautifully, as Rasmus has shown, that each one of those elementary data matrices, remember, or data tensors, really, those rank one things, those elementary pieces of information in the data, one-to-one map to the signatures of different kinds of chemicals in the mix. So essentially, once we find those patterns, each one of them is the signature of a unique signature of the chemicals in the mix. And this way we can essentially uncover what are the chemicals in that mix, right? And so that's extremely useful from, food science to kind of, bioinformatics and cancer, early cancer diagnosis, right? And so this is amazing. And this is one example where the data just screams for this kind of analysis, right? And there are such examples in machine learning and data science, but this is one thing that has been kind of the northern star of anybody who starts thinking about tensor analysis in any kind of given field. And so what are we let's go back to the social graph application, right? What are we looking for is essentially those kind of blocks where you see, oh, those people and those people communicate with each other under those means of communication, right? So those are essentially groupings of people and means of communication that we are seeking to identify. And there's a lot of scary math in this slide, but you can ignore most of it, and you can look at this picture up here, right? So this picture up here is nothing but what I was telling you before, which is you have each one of those triplets of vectors is essentially one elementary tensor, one simple, the most simple pattern you have in the data. And what you're saying here is that take this data and break it down into R, a certain number of those elementary pieces. And in this way, we can actually identify those groups of, those communities of people, all right? I am going to kind of skip a few details here just in the interest of covering more applications and just go into this kind of newer work that we did with one of my former PhD students here, where we were looking at not just what are the groups in a network, but what is their shape as well, right? And you can think of it as, let's say you have a social network. If you have a group of friends, they will probably all be connected with each other, right? But if you have a famous celebrity or, Instagram influencer or whatever, they will probably just be in the middle, and then they'll have a bunch of folks connected to them, right? And so what we call that a star graph. And it kind of looks, because it looks like a star. It has a node in the middle, and it has a bunch of folks who are not necessarily connected with each other because if two people like the same celebrity, it's not super likely that they're friends, right? And so we analyze the network of airports, where basically two airports are connected with an edge if they have a flight connecting them, right? And we found this interesting phenomenon through this analysis where basically there's two kinds of airports and two kinds of emerging structures that connects them. So if you have big hub airports for major airlines, then what you get is basically star-like structure, meaning that you have, let's say, Amsterdam, and then a bunch of KLM flights go to Amsterdam, but then, from there, you gotta go off to, let's say, Madrid or Athens or Vienna, right? And on the flip side, or you say you fly to Paris, and then from Paris, you go to other places, right? Whereas in low budget, kind of, low cost airlines, they kind of have this flying from everywhere to everywhere, right? So they fly from smaller airports, cheaper, smaller airports, and they kind of have this kind of what we call a clique structure, where basically, like, you can tell it's kind of more of a everybody connected to everybody else, as opposed to here you have all those hubs and you have this star-like structure. So this is one kind of interesting kind of analysis that, this was a public data set that allowed us to demonstrate the power of extracting this kind of information. And of course, if we were Facebook or Meta now, this would be useful information to know and understand the shapes of communities, because that tells us the dynamics of communities, right? And so this is something that is useful in multiple different kinds of scenarios. I'm just going to skip that. And I'm going to go to now a different application that we've looked at, which has to do with fake news and misinformation, right? I suppose all of us are very familiar with the term. Many of us, probably all of us, have seen examples. This is a famous example where a rumor emerged that a Starbucks establishment in Atlanta had despicable things in their coffee, and that can, if it takes off, this can actually, hurt business, right? And so this is, even though kind of somebody may say, oh, but it's kind of a funny, innocuous, kind of, rumor or whatever, but it can actually hurt a business, and it can make the stock drop and so on. And so it can have ramifications in the real world, right? This is one of my personal favorites. Does anybody know what this is supposed to be? Any guesses? No, just the whole thing, like this whole picture. Oh yeah, Caitlin got it, exactly, yeah. So this is supposed to be the chip, the 5G chip that was included for free in the COVID-19 vaccine. And this is supposed to be a diagram, right? And clearly, because I got the image from Snopes. Snopes is a website that evaluates the veracity of a particular rumor or a particular piece of news. It says false, right? So it kind of gives it away. But it gets even better, because it turns out that actually this is not the 5G chip, but this is the schematic for this distortion pedal. It's called Metal Zone by Boss, which I actually used to own back in Greece, but I do not own anymore, although I still love to play guitar. And this combines, a lot of things that I like. I like guitar, I like analyzing data, and so this is kind of, I like this example a lot. But this example is also really telling, because by kind of combining information and kind of understanding that, hey, this schematic looks a whole lot of similar to like the schematic of this pedal, maybe that's not, what's going on here, right? And so combining all this information, not just relying on a text that may be saying, oh, be careful, people, we're going to be microchipped and this and that, may be able to give us a better, more concrete answer in understanding quickly whether a particular piece of news is trustworthy or not, right? And this is a really challenging problem, because, of course, it's sometimes fact-checking happens after a new piece of news emerges, and there is a time in which it's unknown and unclear whether something is true or not. But there are certain types of misinformation that are particularly kind of ripe for being able to be detected, especially, let's say, things that are of the form of clickbait. And you would argue whether that's misinformation or not, but you're all familiar with kind of, articles that say, oh, you won't believe what this star of this movie looks like. And then you click on it and it just look like, normal. And you were like, why did I click on this? Well, then those people get, the website gets ad revenue from you clicking, right? And so, like, if you were to only read the title, then you'd be like, well, that person is probably really messed up now, because why else would they kind of say, oh, you wouldn't believe what they look like, right? And so in some sense, this gives a false sense of the world. And so those kinds of things, we can use machine learning and AI to kind of understand and detect quickly. But to close the gap, we also need fact checking. But just the point I'm trying to make here is that introducing the different aspects of an article is very important, right? So in addition to the text, right, we have other kinds of content, right? We have images, we have videos, and putting all those together can actually, as I argued just before, can help us do a better job, right? Many times, understanding who is the author, is there an author, right? Is it signed by someone or is it anonymous, right? Is there a reputable outlet that is standing behind this piece of information, right? Introducing all those features into the algorithm can certainly help us figure out whether, the likelihood of something being trustworthy or not. The medium itself, what does it look like? Does it look like something that has crazy ads for back pain and tax evasion and this and that? Or does it look like a normal news outlet, right? And also, very important, what is the social context in which this news article is being shared, right? So if you get to know me, you'll understand that I'm a coffee enthusiast, right? And so if you know this fact about me, then if I tweet that, oh, according to science, coffee makes you immortal, then maybe you'll be like, well, this guy, he's like that, don't trust this thing, right? And so integrating all those kinds of aspects can help us do better in understanding fake news, right? And so what I'm going to kind of flash forward to is an interesting finding we had that integrates kind of the visual and the visual and the domain aspect of things, right? And so the question was, if let's say we just look by looking at the website, can we tell whether it's likely to be misinformation or not? And it turns out that the answer is yes, right? So we collect the data and we labeled them. Well, we didn't label them ourselves, but there's public repositories of well-known and kind of notorious spreaders of misinformation that are kind of vetted and neutral. And so we did not want to interfere with who decides what is misinformation. And we kind of also try to restrict ourselves to the most egregious kinds that are kind of not debatable. It's not that it's some kind of bias in the view of the article and someone can call it misinformation, but it's more like, a clickbait or something that's completely false, right? And so we used convolutional neural networks, we used deep learning, basically. We used the same kind of technology that your phone uses to tell you whether this is a picture of a dog or a cat. Pretty similar. If not, actually, the Tensor one was working even better because it was more lightweight and more capable of working with this kind of data. And so we were able to show that with, roughly 85% accuracy, if you will, we were able to detect something being misinformation. Of course, this is not something that I would advocate being released as an automated tool for kind of blocking websites or anything like that. But the question that it answers is whether the design choices and the way that the website is structured in certain domains has any signs that can help us detect misinformation. And think about it, many times there's all those websites that look exactly the same because they are kind of produced en masse, and they kind of all propagate the same kind of information. And this is the kind of stuff we're looking for. Or there's a lot of websites that have tons of different ads or pop-ups, and this kind of is correlated with, you know, some less kind of professional designed websites. And of course, that does not mean that all non-professional design websites are misinformation. And that's why this is just an academic exercise for understanding what kind of features, what kind of things are signals for this, right? And so I want to be clear about that. Now, this is the segue here is very important because, as I said, because of the fact that like a sloppily made website correlates with misinformation, that does not mean that it's always misinformation. And so what this tells us is we need from our tools that we develop, you know, to be accountable and transparent and explainable, right? And what a really popular example by Samir from UC Irvine is the following. So let's say that you develop a tool that is able to detect it tells you detect wolf versus husky, right? And it works perfectly. It works 100% of the time, right? But quickly you realize that if you try to explain the decision, then in order to predict wolf, it looks at the snow. In order to predict husky, it looks at the grass. And so turns out that the AI algorithm, all it did was, well, you only showed me huskies in grass. You only showed me wolves in snow. And so what I'm going to do is I'm going to ignore everything else, and I'm going to look at the background, and I'm going to let that decide. And so this is a problem, right? Because what happens if a wolf comes to our lawn and attacks, you know, the house? That this is the case where this would fail, right? And so that underscores that, you know, if we have this kind of explanation, then we could intervene and say, you know what, ignore the background, focus on the foreground, and then try to understand what distinguishes a wolf from a husky, right? So explainable AI is extremely important. We've tried to do something like that in explaining decisions for COVID misinformation, and what we did was basically trying to use reference documents, meaning published literature, published articles, manuscripts that talk about different topics, right? And so we essentially are saying this is misinformation because, and here's why. Here's this paper says that, oh, this is how this happens, and that's why what this article says is false, or that's why what this article says is true, right? And so I know I'm running out of time, so I'm just going quickly through those examples, but basically we are using an AI system that tries to learn what we call an interpretable and explainable space in the space of those reference documents that we can use as explanations. And then quickly, two more applications, and then I'm done. This is a really exciting one, and it has to do with a collaboration with the LIGO, or the Laser Interferometry Gravitational Wave Observatory, which is one of the most sophisticated scientific experiments on the planet right now. It brought us the detection of gravitational waves back in 2015 and the Nobel Prize in Physics in 2017. And so Einstein predicted that when two masses orbit around each other, they emit what we call gravitational waves, which are small disturbances in the space-time continuum. And we were able to detect them back in 2015. And the problem is that they're so ever so slightly small that many other things can appear as gravitational waves, but they're not. And those are what we call glitches in the detector. And we need to understand when and how those appear. How do we detect them? How do we actually fix them and remove them from the scientific experiment in order for us to get clean signal that can let us explore the universe? And just one pitch here is that gravitational wave science can let us look at the universe in a different way, because essentially objects like black holes do not emit any light. So we cannot really study them with traditional telescopes, but they emit gravitational waves when they are orbiting around each other. And so this allows us to look at the universe in a whole different way. And this is a super exciting project that we're doing in collaboration with Barry Barish, who is one of the Nobel laureates from the discovery. last but not least, and then I'm going to stop in a couple of minutes, I think should be, is that okay? Is adversarial attacks, right? And so probably you've seen this picture. This is a panda, and then what happens is your AI says it's a panda, but then you add a little bit of noise, and your AI freaks out and says, no, it's a gibbon, right? And this is not an academic exercise. Somebody actually put those stickers in a stop sign, and Tesla's autopilot thought, it was actually like actually they do it in a 25-mile-per-hour sign, and then Tesla thought it was 50 miles per hour, right? So this can happen in real life, right? So how do we evade those kinds of attacks? We have a lot of work in showing that understanding what are these elementary patterns in the data and removing everything else actually sanitizes the data and removes the attack. And so we have a lot of work in different kinds of applications and domains that help us understand that and basically find out what is the real signal and what is the attack and push them apart. I'm going to kind of move forward and just thank all the really photogenic students for their hard work and our funding support from all those generous funding agencies. And thank you all for sticking around and for your questions during the talk, and hopefully we have some time now. So, I think my slides just died, but you can, please, if you have any questions, now's the time. My email address is also at your disposal. So if you would like to, if you have any questions or you kind of don't want to ask now or you come up with any questions later, feel free to shoot me an email and I'd be very happy to chat. I can put it on the chat now. You're very welcome. Great. So yeah, I think someone unmuted. Yeah. You're very welcome, and thank you for having me. It was a pleasure, and looking forward to interacting with anybody who has any questions or wants to learn more about all this stuff. And I hope you all have a great, relaxing, long weekend.